the talk, Advances and Perspectives. We are a new group. We are starting to have a working machine. So I want to present, let's say, very detailed research results. I will present you the advances that we are having in the Ultracold matter laboratory and the perspectives, the things that we want to do. So let me start by saying that ultracold fermions are very interesting many-body systems because they are very controllable. And also because fermions, they are a very controllable system which has a very intimate relationship with condensed matter physics. Okay? So at ultra-low temperatures, what we know is that identical fermions do not collide, do not interact, because the polyblocking will make them almost an ideal gas. However, if we produce a spin mixture, then the spin mixture will interact. Here, I'm considering that the system is so cold that the interaction is through S-wave scattering, which is parameterized by a single constant, which is a scattering length here. And what we know is that this scattering length, which characterizes the collision between two fermions, it depends on magnetic fields in this way. So this is a very nice tool. This is something called feedback resonance, and what you can see is that the constant that mediates the interaction depends a lot on external magnetic field. So the fact that we can change the interactions using an external field makes possible the production of pairs. Okay, and depending on how the interactions are, we will have different nature of pairs. So for instance, if we have that the scattering length is positive, which means that the effective interaction is repulsive, it is a molecular state is possible, and then the pair of fermions become a boson, and they condense, and we can produce a Bose-Einstein condensate of molecules. Instead, if the magnetic field, if the scattering length is negative, what we have is that the bound state is something equivalent to a Cooper pair, like in superconductors. So what we produce is a Fermionic Superfluid similar to the BCS state in superconductors. And of course, there is also a regime in which the interactions diverge, they become very big. We can also have pairs, and this is known as the BEC-BCS crossover. So what it is very nice with fermions, in contrast to bosons, is that we have access to different superfluid regimes, different quantum macroscopic states with different natures that we can explore. And in fact, there is a very nice experiment from the group of Wolfgang Ketterle in which they demonstrated that the fermions in all these regimes are superfluids because they can observe quantized vortices across the whole BEC-BCS crossover. So within this context, and because this nice degree of control that fermions present, we have proposed the building of an experiment at the institution. And basically, initially, the idea was to create a very flexible and versatile system in which we could produce all optical ultracold samples made both by lithium-6, which is a fermion, or also lithium-7, which is a boson. And we also want to have large optical access, because in this way we can do a lot of things. As Karina explained, the way we interact with and manipulate atoms is using light, so it's better to have a good optical access and have a lot of laser beams available to interact. And for instance, we would like to have different imaging capabilities, versatile optical trapping potentials, just like Karina explained, to have 3D potentials, 2D potentials, lattices, whatever we want, and also to shape different potentials using other tools and create, for instance, disorder or any other kind of optical potential. So this is what we wanted to do. So let me present you what we have now and how we are moving towards that direction. So basically in our experiment, we use a stable fermionic isotope of lithium, which is lithium-6. The Fermi mixture that we use is these two hyperfine states. Well, it's the same hyperfine, but we have the two magnetic projections. Okay, And it is very nice because the phase-back resonance that I just showed to you is exactly the one that corresponds to this state. Okay, this would be the ultra-high vacuum system that we have. So here we have the oven in which we heat up the atoms, and the atoms will move towards all these tubes up to the science chamber in which we perform the experiments. Of course, the system has other parts that I won't go into the details right now. I just want to tell you that we have cooled both isotopes, so we have the possibility of cooling down fermions or bosons. But of course, everything that I'm going to show to you now, it concerns only to the fermionic species. This would be the cut of our main chamber. As you can see, we have a lot of viewports that we employ to produce the magneto-optical trap and manipulate the atoms. And also we have magnetic fields, so we have a set of magneto-optical trap coils to produce the magneto-optical trap, and also another set of coils which we will use to produce the phase-back resonance. So these are this is the level scheme of the lithium atom, the lithium-6. As every other alkaline, you have these two lines, the lowest energy optical transitions, the D1 and the D2, and we use the D2 line. We use these two transitions to produce a magneto-optical trap. So this would be a picture of our magneto-optical trap. Right here in the is this bright spot, and we employ optical molasses to cool down the sample. So the green curve here, what you see here, is the theoretical limit, which is known as a Doppler limit. So in typical experiments, it's possible to go even beyond, but as you can see, this curve would be the temperature that we achieve using these transitions. And as you can see, we are way above. And the reason is that the lithium natural line width is larger than the separation of the hyperfine states. So this makes this cooling scheme very inefficient. So what we do is to use the D1 line. So again, I have the same transitions that I showed before, but now I'm giving you details here. And what we employ is a second optical cooling technique known as gray molasses. In this case, what we use is the light, but tuned to the blue from the transitions. Basically, the mechanism here would be a velocity selective coherent population trapping mechanism. I don't want to go too much into the details, but what I want to say is that we are able to cool down the temperature of our sample, which in the magneto-optical trap is originally at 7 millikelvin, up to 45 microkelvin, which is way below the Doppler limit. So this is a very good starting point to continue with the cooling mechanisms. So the next step is to transfer the atoms. So here you see a top view of our chamber, and then what I'm showing here is an optical dipole trap in which we trap some of the atoms that we have cooled previously. And of course, we have also the phase-back field here. And the phase-back field, of course, has the purpose of accessing into the phase-back resonance, but it's not the only thing that we do with this field. We set the field right in the limit in which the interactions diverge. So the interactions are very strong and the evaporative cooling becomes very efficient. But also the presence of the magnetic field will split the levels of the ground state. And in this way we can create the spin mixture that we will use to associate the pairs and produce the superfluid. But also, I want to say this just a detail, the phase-back field has a small curvature that helps us to confine the atoms in one of the directions. Okay, so what I'm showing you here is an absorption imaging just like the one that Karina showed previously. And what you see here is this sphere of atoms. This would be the atoms from the magneto-optical trap. And then you see this line, way more, a denser line here in the middle. This would be the optical dipole trap. And it is in this dipole trap in which we can perform the evaporative cooling to reach the quantum degeneracy temperatures. So basically, at the end of the evaporative cooling process, we have a very elongated trap. We have a cigar-shaped trap in which the frequencies, what I want to say here is that the trap is 15 times larger in one direction than in the other. It's a very elongated trap, but it doesn't matter. We still have a three-dimensional trap with a superfluid inside it. Now we can decide which of the superfluid regimes we want to explore. So for instance, we set the magnetic field somewhere here, and what we obtain is this picture. So what we are seeing here is 3 absorption images of the lithium gas at decreasing temperature. So here what you see is this very clear spot. You cannot see anything, but this would be the density profile. It is a Gaussian, but as we cool down, it appears a very sharp and different distribution in the middle, and as we cool down even more the temperature, the most of the gas will follow this very sharp distribution. This is the signature of Bose-Einstein condensate. So what you are seeing here is the first Bose-Einstein condensate in Mexico. I'm very happy to say that exactly this day, 1 year ago, we produced our first Bose-Einstein condensate of molecules in few hours, actually, in the night. This is the best time to work at lab. So this is important for the students to take into account. Okay, and maybe we can go for a beer later. But of course, there is more, because fermions are nice because of this. We can produce also other regimes. And for instance, now I'm showing you 3 pictures at very low temperature, but at different interaction regimes. And what you can see is that when we are in the positive branch of the Feshbach resonance, we have again our very nice Bose-Einstein condensate of molecules. But as we move through this curve, the density profile of the cloud changes a lot. So we have, what you are seeing here is a picture of 3 different superfluids, Bose-Einstein condensate, a sort of PCS superfluid, and then a very strongly interacting superfluid right in the middle. This, I'm also very proud to say, that would be the first ultracold fermionic system in Latin America. Of course, in Brazil they made the first Bose-Einstein condensate in the Latin American region, but they up to now only work with bosons. And this would be the main result that we have in our laboratory now. Let me tell you what we are doing now. So this is the picture that I showed you about the Bose-Einstein condensate of molecules. We want to improve the quality of our image, and what we have done is something very simple. We put a spheric lens with a very short focal length very near from the atoms. So we have a way better imaging system with a much higher resolution. So previously we had a resolution of about 8 microns. We couldn't solve anything smaller than 8 microns. Now our resolution it would be at 2 microns. So if you just for compare, this would be a picture of the condensate inside the trap. This is a picture of the condensate after 25 milliseconds of expansion. So the quality is way better here. The scale here would be 100 microns against 500 microns here. But there was a question over there about how destructive the imaging system is. The absorption imaging system is very destructive. It will heat up the sample and destroy it. So since we want to observe the dynamics of the system, we have also developed and implement a non-destructive phase contrast technique, in which what we observe is how the phase of the light that passes through the atom changes. And this picture is not destructive. So this is what we are optimizing right now. These are pictures from our lab. And of course, I don't work alone. I have a great team which is working with me. So this is a picture of the people that is currently working in the lab and the responsible from all the nice results that I showed to you. So let me introduce you Jackson Poveda. He's another researcher working in the lab, and we have actually 7 students right now. Diego and Eduardo, which are master students, and Andres, Sebastian, Melanie, Karen, and Javier are undergraduate students. But of course, it's very important to mention that this is possible because a big effort that Rocio and other researchers have done to construct a national laboratory from which our laboratory makes parts. So this is Rocio Jauregui, she is the leader of the National Laboratory for Quantum Matter. We have also a collaboration with other theoreticians, Victor Romero and Rosario Paredes from our institution. And here I want to mention also my collaboration with Giacomo Roati from the University of Florence. He has helped us a lot in the building of our experiment. And of course, we also have technicians in electronics, all the instrumentation and the electronics that we use in the lab. Well, a part of it is developed by Carlos. And also my other experimentalist colleagues from different labs, but we together have built all the infrastructure, the basic infrastructure to make possible our laboratory. And of course, it's very important to say we have a very strong institutional support. Okay, so this is what we have. Let me tell you a little bit of what we want to do. Okay, so I already mentioned that if you have a Bose-Einstein condensate, like the one that is trapped here in a dipole trap, this image is from this article here, and you rotate the trap and you transfer somehow angular momentum into the atoms, you can produce quantized vortices. Okay? So in this picture you are seeing a vortex lattice in a Bose-Einstein condensate, and here, sorry, it would be the same vortex lattice but in a fermionic superfluid across the BEC-BCS crossover. So these pictures were like the definite demonstration that these systems are superfluid. But of course, a nice question that we could make is if it is possible to have turbulence in these systems, and the answer is yes. And the main ingredient that you would need to have this is a lot of quantized vortices. This is not a new question. The first person in asking it was Richard Feynman in the 50s, and he imagined turbulence in a superfluid. Remember that at that time the only available superfluid in a lab was liquid helium, and he used to imagine the turbulent state like a collection of tangled, very disordered vortices. So this is just an artistic representation of the system. And few years later, William Vinen was the first one, his group was the first laboratory in observing this phenomenon, again in liquid helium. And since then the phenomenon has been extensively studied in superfluid helium. Okay, so one question is, why do you want to do this 60 years later again? Well, a very important reason is that helium presents an important limitation, which is the size of the diameter of the vortex depends on the density and on the interaction is inversely related to the square root of the density of the system and the interaction. So helium is very dense. It's about 10 orders of magnitude more denser than ultra-cold gases, and also it's very strongly interacting, and the result is that the diameter of the vortex is less than, it's 0.1 nanometers. It's a sub-nanometer object. So we cannot observe the vortices optically. The same distance, I mean the same quantity for the case of a dilute gas like the ones that we have in the lab is of the order of 1 micron. So the vortices are way bigger and they are optically observable. So in this sense, one important precedent is the theoretical work from Makoto Tsubota, who showed that turbulence should be possible in a Bose-Einstein condensate. And he also showed, I'm not explaining, I'm not giving too much details, but what he demonstrated in his calculations is that the statistical behavior of quantum turbulence should be exactly the same than in a classical fluid. And this is quite incredible, in my opinion. So what I'm showing here is how the energy is distributed along the scale, the length scales of the system. and it follows a power law, which is exactly the same, with exactly the same exponent that you would have in a classical fluid, which means that turbulence is we already knew that turbulence was a universal phenomenon, but it's very universal. And of course, 10 years ago, Professor Vanderlei Bagnato from the University of São Paulo in Brazil was the first, in his laboratory, this phenomenon was observed by the first time in an atomic Bose-Einstein condensate. But again, all these measurements have been done with bosons. Okay, we want to do it with fermions. Now let me tell you a little bit how we want to do it. Again, we want to use the interaction between light and matter to steer the condensate. And the idea is to steer the condensate, to shape it along two perpendicular directions. Initially, we could use a configuration with crossed A-lines, with optical modulators. But if it doesn't work, we have also another option to use another device to manipulate dynamically the light. We want to use something equivalent to Bragg spectroscopy to measure how the energy is distributed along the length scales of the system. And since the problem is very complicated and we have problems, we can simplify the problem. So we can, instead of using a harmonic trap, we could produce a box potential, just like Zoran Hadzivavic have done in these two papers. Or we can explore also the 2D geometry, like Brian Anderson or Professor Shin from South Korea have done as well. But again, these works have been done up to now only with bosons. So basically what we are proposing is to put together three very interesting research lines: quantum turbulence in one side, fermionic superfluidity in another side, but also strong correlations or strong interactions in this case. So what I can tell you is that there is, in the intersection of these three areas, there is this white spot which is nearly unexplored, even from the theoretical point of view. So we think that one of the first things that we want, one of the first measurements that we want to do is how the energy distributes and dissipates as a function of the scattering length. And finally, of course, I want to change the topic a little bit. We are in a quantum technologies conference. I just wanted to say that Fermi superfluids, even if we are not so connected with quantum technologies, I think Fermi systems can contribute to improve the quantum technologies, because they are an excellent framework for the implementation of quantum simulators. So I just wanted to mention a nice example, which is quantum transport. So I'm showing here the work from the group of Massimo and Lucio in Italy. What they have done is produce a Fermi superfluid and divided with a very thin barrier. And what they observe is a Josephson oscillation. So this is a typical quantum transport phenomenon. There are other works. In this part of the slide, I've shown you the work from Timman Eslinger at Switzerland. What he does is that he produces two fermionic superfluids and joins them with a one-dimensional channel, and they observe the quantization of the conductance of the fermions across this very thin channel. So these are very nice experiments. And finally, I want to jump into the conclusions. So to say that we have produced superfluids across the BEC-BCS crossover. We are we are developing right now nice imaging systems, and in the near future we want to generate and study vortices and quantum turbulence. And in this way, I end my talk. I want to say thank you to the institutions and thank you to you.
Thank you very much for this great talk. So we have time for a few questions. Please first. helps.
Well, this is really just wonderful work. I think it's really quite astounding that the first thing you do is a Fermi gas, because it's not easy and the results look quite beautiful. I'm wondering about the phase contrast imaging. Now, as we know, the so-called non-destructive imaging is never non-destructive, but the images you showed look really good. So what's the loss per image?
Okay. Let me go back to the image. Sorry, okay, it's
There it is, yeah.
So actually, it's a little bit disappointing. These are not pictures of the same, of this. I mean, we are just demonstrating that we can observe that we can use the setup. So it's not the same cloud in all the pictures, but we are able to take, let's say, we estimate that when we are in the case in which we are more detuned, we lose less than 10% of the atoms. So we can do 5 or 6 images of the same cloud and still say something about it.
Thank you. One more question here.
Maybe it's not a very clever question, but is there a way, or how do you define the borders of the DCS crossover? Because you have the middle, which is for sure the resonance, but the border seems like arbitrarily defined, right?
No, okay, it's actually a very good question. So I didn't show here. So yeah, you say, yeah. How do you know where the borders are? Well, the important parameter here that I'm not showing here would be the scattering length, of course, but also the Fermi momentum. So the figure of merit to know where you are would be the Fermi momentum times the scattering length. This would be a dimensional quantity, okay? Then the BCDCS crossover, in the literature you will find that it is the region between you take the 1 over that amount, okay? And then you have the strong interacting regime. Here, you will have 1 over KFA equal to 0, okay? And then this interval will be the interval between -1 and 1. And since the Fermi momentum depends on the density and the number of atoms, then I cannot tell you which is the magnetic. First I have to produce a superfluid in order to tell you exactly where the DC-DCS crossover is.
Okay, thank you very much. So we have no time for more questions. So
Thank you.
Thank you. Yes, let's